So, okay, now, so what you'll see when you watch the video is you'll see what's on the projector and my voice. You don't see me. I discovered many years ago I used to record lectures for online classes where I never met the students face to face, and I was told after a while that they didn't like the fact that my seeing me took up too much of the screen and they couldn't read what was on the screen was too small. And in particular, I had a number of students that were watching the videos on iPhones and iPads and iPod touches and things like that, little Android tablets. As a result, the screen's tiny anyway, and then a fourth of it is my picture. They cut the slides down to about half the screen. So, and I do a lot of I'll be doing software simulations where you need to see the screen. So, but today I'm basically just going to go through these slides. I'll make these slides available through the e-learning probably in the next week or so. I don't have them up yet, but I will make these slides available. These slides are from a textbook by Floyd. I have the book, but it's too big to put up on the e-learning site. So, if someone's got a thumb drive, I can, make it available to you. The slides come from the 7th edition. What I've got available in PDF form is the 11th edition, or is the 9th edition, excuse me. And I have another book that I use for this class by Tochi, and what you'll find is that I bounce back and forth between books. So I use 2 books for this class. I'm not making you buy them. We'll make them available other ways, but they're relatively expensive books if you were to buy them out there. So I will use some slides from Floyd. I'll use some from Tochi, and I'll use some of my own notes that's there. I suspect they're looking for their classroom. This one's fairly easy to find, right? You are in the digital course, right? This is the digital course. Okay. So, I have to assume there's more than 5 people in this class. There might be less than that, but let me just kind of go through my background. Obviously, I'm not a local instructor. Some of you have probably seen me around. Some of you probably talked to me off and on. I just moved to Malaysia about a little over a year ago. I came here at the end of June of last year. I spent 6 months working in Cyberjaya with Mike on the aerospace blueprints. I lived in Malaysia back in the late 1990s for a couple of years. I taught at UTHM. Back then it was called ITO, Institute of Technology Tuna Zain. Now it's just University Tuna Zain up there. Welcome. That's there. Up there. So I taught there for about 15 months or so as an instructor, and then I taught for a academic year at Uniten there. My home base I just recently retired, was Purdue University back in the U.S. I was there for a total of about a little over 30 years. So while I was teaching in Malaysia back in the 1990s, I was actually on loan. I was still an employee of Purdue. My wife's Malaysian, so I've had ties to Malaysia ever since then. So I've been, after I taught here in the 1990s, I came back to Malaysia pretty much every year for at least 2 weeks to a month to 2 months, something like that, usually in the summer vacation. So I've spent a lot of time in the country. I don't speak the language. I am not very smart when it comes to language. My wife just says I'm lazy. So she just says I walk malas. So she gives me a hard time about that, but that's all right. My problem is I can't hear myself talk at times, and my pronunciation is bad. I also can't sing because I don't hear my own voice. So when I hear lectures and I hear the recording, I actually hear what I sound like. That's one of those things that some people have So I have no musical talent, and I have no talent when it comes to learning foreign languages. But I have other skills, mathematics, computers, and things like that. I've spent a lot of time back and forth between industry and the university. That's there. When I graduated, I went to work for a company in the U.S. called Magnavox for a few years. And Magnavox was in the military electronics industry, the aero defense industry. I worked on anti-submarine tracking equipment. That's there. I did some work in digital signal processing. I also worked in test equipment design. I did things there. I've done a fair amount of consulting. I worked for General Electric for a short while, doing some work on their jet aircraft engine controls, doing test equipment design for that particular group. That's there. I've done some work for Navistar that builds trucks and doing, putting sensors on trucks and measuring stresses. That's there for predictability. And then I spent a long time, probably 15 years off and on, every summer a sabbatical, and probably 10, 15, 20 hours a week working for a company called the Indiana Microelectronics Corporation, where we did custom chip designs of digital electronics, usually using VHDL. And I did some work with a lot of work with microprocessors as well. So my background has completely been digital. I really have not done much outside the digital realm. So I'm a little bit of an oddball when it comes to the ICO staff, because most of those folks are all electrical power people. My background has been digital, and in particular, it's been in the design area. I've done work in manufacturing. Before I went to the university, I worked in a brake shoe factory where we made brake shoes for cars and trucks and clutch facings and that type of stuff. It's the heavy-duty industrial. I decided I didn't like that. That's why I went back to the university and studied electronics. So, we're here to learn digital electronics. Digital electronics is probably not bad for you guys. I also teach the microprocessor and the microcontroller course where they do a lot of programming. Everyone seems to hate that class. This one here isn't so bad, but it is different than some of your other courses. The good news is this course uses no calculus and very little algebra, so there's not a lot of math in this course. That's there. So we're going to kind of go through the idea of digital electronics, and I'm just going to kind of go through these slides. I've been through them 20, 30 times. That's there. This is basically what you would see if you're measuring an analog quantity. In other words, this is the temperature versus time of day. Obviously, it's from an American textbook because the temperature is given in Fahrenheit instead of Celsius. That's there. And you can see that at midnight, the temperature was 74 degrees roughly. It dropped down to about 70 at 4 or 5 in the morning, and it got to like 96 at the peak of the day, which that part could almost be Malaysia. That's there. Although it doesn't get down to 70 at night. It usually gets only down to about 76, 78, I notice at night. That there, when I'm talking Fahrenheit. But you can see, the main thing what you're seeing when you're looking at an analog quantity here, and I tend to sit down a lot while I talk, simply because where's my pen? There's my pen. Is that the voltage here? Oh, I don't have this in slide where I can write notation. There we go. Put the pen on. I don't want the laser pointer. Welcome. Well, I don't see the pen here. Okay, well, regardless, what we've got here is you can see that this voltage takes on every value in between, right there. When we move signals from analog to digital, two things happen. One is we quantize the data. When we say quantize it, we mean we're going to have distinct values in between that there. We cannot have, for example, a temperature of 90.2346. We have to have certain values in between. We have various levels there. So as we look at the slide, this is where we're looking at Now this actually is showing that we have certain values right here. We don't have the values. And the other thing is we sample up there. So this is the sampled data right here. And we're also going to end up with usually an integer number representing this analog value right there. It's going to be an integer binary number made up of zeros and ones there. So when we sample the data, we lose all the information in between these hours. Now, in this particular case, we're grabbing the data, we're sampling it once an hour right there. We can sample it every 10 minutes if we want. We can sample it every 30 seconds if we want. It's just how much data do we want to store. You know, we do this a lot with, for example, music. When you look at music today, my generation grew up with phonograph records and tapes. And phonograph records and tapes are analog recording devices. Your generation grew up with CDs and MP3s, right? Those are digital devices. So when you look at CD quality sound, it has been sampled at 44 kilohertz. So 44,000 times a second, the sound quantity is measured and stored there in some form. That's there. Usually in just a computer file initially when they do the recording, right there. The other thing is that you have a certain number of bits that represent musical sound. CD quality sound is roughly stored at 24 bits of resolution, and we'll get into some of that later. We don't do a lot of that discussion in this course. But what you do though is when you take music and you store that digitally, you're going to lose the information in between the two samples, and you're also going to lose the precise amount of, the values in between right there. You look at this graph here, and you look at this graph here, they look the same, but there's more information in the first graph. We've lost some of the information when we move to the second graph. Now I can interpolate. The word interpolate means I can guess the value in between right there, because I know the temperature right here is roughly 87 degrees, and the temperature here is 91, so I'm guessing that there's a straight line in between, and I can kind of estimate what the temperature is, but I didn't record it. It's gone. But when I look at this graph, I've got enough data that I can pretty well estimate the temperature any time of the day, right there. But in this particular case, this is very slow-moving data, so sampling once an hour is enough. If you're talking something like music goes anywhere from the human ear hears from 20 hertz to 20 kilohertz, 20,000 hertz, right there. And you've had some courses in AC there, so you know what I mean by 20,000 hertz versus 20 hertz. 20 hertz is very slow moving there. That would be like a bass drum or the low end of a bass guitar. 20 kilohertz would be like a female singer that can almost break glass. A very high pitch right there. So music is also very irregular. It's not a nice smooth sine wave, so it's a little harder to interpolate. That's there. There is such a thing called, there's a theory in sampling music or sampling anything that says as long as you filter everything past half of the sampling rate, that you can restore it back close enough. Now, music we're saying is 44 kilohertz. Something like a telephone's 3 kilohertz. The sampling rate is 8 kilohertz. They sample at 44 kilohertz. They low pass filter down to 3 kilohertz. Music you low pass filter down to 20 kilohertz, right there. We're not going to do much of that discussion in this class. It's just kind of what's going on here. But this is basically what happens in an analog system. You have a microphone that picks up the original sound waves. These are all analog. Here's our analog signal. It goes through an amplifier. This signal should look the same as this signal, only this one's larger. and it goes through a speaker right there. Very straightforward process. And this is the way tapes and phonograph records and a PA system works perfectly. When we look at digital, we go through a different process. Now this just shows the playback operation and only shows one channel. But we have a bunch of ones and zeros here. That's what's stored on the CD drive. CD drive is basically a foil type coating on a disc that has got pits in it that reflect light or don't reflect light. If it doesn't reflect light, it's a 0. If it reflects light, it's a 1 right there. So we store the zeros and ones on the CD. We run it through a digital to analog converter. That then gives us our analog signal back right there, and then it goes through a linear amplifier. You do this all the time. I mean, you play an MP3 on your phone, this is the process. The only difference is instead of coming from the CD, it's coming from the MP3 file on your phone. And I know that that's probably 99% of your music is listened to, right? Either you buy a CD and you rip it and put it on your phone, or you download it through some other channel, or you buy an MP3 disc at some place or whatever. I mean, but you got an MP3 file that you're going to read the data and going to there. Now MP3s are a little bit different because that data is compressed in order to save space there. So there's also another step in here on MP3, and that's the decompression stage. So MP3, you also lose a little bit more information because that's compressed data. Again, we're not going to get into that in this class. That's a very advanced subject talking about music compression and video compression. That's there. So that's there. But we've got, this is the process there. All I'm worried about right now at this stage is the process of going from digital to analog. Right there. Now, when we look at Megatronics type controls, we are talking about a electronic control, electromechanical, and some type of robotic control. So in other words, we're using digital information in order to control a piece of hardware right there. So there. And normally we're using things such as servo motors or stepper motors in order to control this particular device. And we can control this digitally right there. So again, I'm just kind of going there. All right, as we go through here, when we look at analog digital voltages, we have this is right here. I'm trying to find my pen, but automatic. Screen presenter view. I don't know why the pen is not being highlighted. Oh, I know why the pen's not being highlighted. Give me a second here. Because I can't save to the file because it's offline. All right. I guess I'm going to have to live without being able to write on the screen. I feel lost here. That's there. Okay. When we look at this here, digital electronics uses a transistors traditionally. Now, when you study transistors, and I assume you did study transistors at this point, or at least look at transistors, there's 3 ranges of a transistor. There's cutoff, where the transistor is turned off. There's the linear range, and then there's saturation, where you've got full current and it can't go any further, right? When you study analog amplifiers, your goal is to always stay in the linear range. Because if you exceed the linear range, up there, and I can't write here, but I can write here, right there. When you look at a transistor amplifier, and I'm just going to show a typical transistor amplifier right here, coming out of here. Here's V out. And there's BN. This is a classic voltage divider transistor amplifier right there. Right there. And when you use that right here, you've got a signal that goes into here. It looks like this, like this, and coming out this particular amplifier, it's going to look like this. It's going to be 180 degrees out of phase right there. But if you drive it into cutoff, you'll flatten this, and if you drive it into saturation, you'll flatten or the other way around. So you don't want to drive it. You want to keep it in the linear range. When we deal with digital electronics, we're dealing basically with a transistor that looks like this right here. Right here. Here's our output right there. And here's our input right here. Right here. And we're just going to turn the transistor on. If we turn the transistor on, we get full current going through here, and we get 0 volts out here. Right? We turn the transistor off, we get no current through here, and we're going to get VCC here. So when it's turned on completely, that's considered saturation. If it's not turned on at all, that's considered cutoff. It's turned off right there. Those are the only two modes in which we operate transistors in digital electronics. They're either on or off. In the analog world, when you took analog amplifiers or electronic devices, you talked about using them in the linear range right there. So as we go back here, when we look at this here, what we've got here is we've got our high, binary 1, it's going to be somewhere around 3 volts or more. Normally it's around 4.5 volts or more, between 4.5 and 5 volts. But I have seen it somewhere less, depending on how much load you're drawing off of it, right there. The low level is 0.7 volts or less. Now that 0.7 volts should make some sense because that happens to be the knee voltage of a standard base emitter diode, right there. So anything above 0.7 volts is going to turn the transistor on. Anything between 0.7 volts and 3 volts is likely not to saturate the transistor. So that's why you have to be between 3 volts and 5 volts here, and below, I think there's some timing going on where it automatically it's supposed to keep me going at a certain pace. That there. That's why it switches here. That there. But between 3 volts and 5 volts is enough voltage on the base of the transistor to ensure that it's saturated, that it's turned on all the way. And you have to be below 0.7 volts to ensure that it's cut off, that there's no current. So that's why we have these logic ranges of a digital circuit there. We have more leeway here on the high than we do the low. So typically we pull things high that there. And most circuits will float high if we leave inputs up there. So we have a couple other things, terminology we're going to go through here. We have rising or leading edges and trailing and falling edges on digital clocks. That's it. We're not going to be using clocks for a while, but we'll come back to this right here. That's the ideal clock. This is what you normally see with an oscilloscope. I mean, that's a pretty dirty clock, but I've seen them that bad right there. And the reason is that you've got resistance on the board, you've got capacitance, you've got inductance, and you're going to end up with some oscillations here, right there. And the pulse width is between the 0.5 and 0.5. The rise time is between 10% and 90%. Those are some terminologies that we'll talk about later on. That's in the ideal world. You do have some overshoot and undershoot right there. This one is actually pretty bad. I don't see very many of them this bad right there. The only issue comes in is if this ringing is above 0.7 volts, that sometimes it can create some problems with the circuit right there. Some other terminology that we've got is that we've got a period which we can measure with an oscilloscope, and 1 over the period is the frequency right there. That's the same as your analog world right there. We have non-periodic waveforms. Now, non-periodic waveforms you will see quite often. You know, especially because this would be, for example, serial communications. Right there. This would be a 1 0 1 0 0 1 0 1 0 1 1 0 0 1. That there. In other words, this could be communications that we're sending out to a printer or something like that. You very likely can see a waveform that looks like that if you're communicating between two different. And then again, some other circuits will give you such an output. That there. So it's not unusual to see non-periodic, especially internal to our circuits right there. We also have something here called the duty cycle, right here. And I'm not necessarily going through the books, I'm just kind of going through the slides right here. The duty cycle is basically the percentage of the time that it's high. And you can go anywhere from 5% to 100% duty cycle. 100% duty cycle means it's always high. And quite often we will use this in a procedure called pulse width modulation in order to do a very low-end digital to analog conversion. And quite often we can use this to control the speed of motors, the amount of power that goes to a megatron on a microwave oven, these types of things, how bright a light is. So here we're looking at about 10% duty cycle, so 10%, well, yeah, they show it between 0 and 10, so that's, 10 milliseconds, and it's on for 1 millisecond, so that's a 10% duty cycle. As I widen the pulse width, I can go to 50% duty cycle, and my light is going to get brighter. This is quite often used to brighten and dim things such as LED lights, right there. It doesn't work for incandescent lights. These are fluorescents. You can't dim fluorescents typically. That's there. So then we've got some. This is an example of here where here's our clock, and here we've got 1 0 1 0 0 0 where we're having serial bit string. That goes back to what we're talking about right there. Now I'm going to kind of go through here a little bit. These are all just the slides. I'm going to pull up the book and kind of go through the sections of the book there. I hope I have that book here. Right there. I'm just kind of going through the slides first. If we look at this right here, this is 0, 1, 2, 3, 4, 5, 6, 7. As far as the output goes right there. And we haven't looked at binary numbers yet. So, matter of fact, I think I'm going to stop the slide right here. There's lots of slides, but they don't really tell the story. Let me pull up this book here. All right. This is the book that the slides come from. This is the 9th edition, and again, I'll make this available right there. So let me kind of go through here and kind of jump to the book and just kind of hit the highlights right there. We've seen some of the slides. We've talked about this before. This is the analog quantity right there. This is showing our quantized and digitized signal right there. Right there. Now, this is what's not necessarily talked about, but in the digital world, we have only 2 bit or 2 volt levels. We're going to talk a little bit about numbering systems here, probably Thursday. I think we meet again Thursday, don't we? Yeah, that's there. And at some point we're going to be meeting in a lab. I will have some labs for this class. That's there. They scheduled me, I think, for both meetings in here, but there's a lab that we can use. That's there. We don't have components, but we'll talk when we get to the lab. We'll work through that there. So we have those voltage levels right there. We've already kind of gone through that discussion here. Here's the formula right here where we look at our duty cycle. So that's why I kind of went back away from the slides and to the book, is to kind of point out where this comes from. Right there. This is our duty cycle. It's the width of our high pulse divided by the period of our signal times 100%. So this is a 10% duty cycle right there. Now, again, here's a particular case right here where we're looking at a timing pattern, and we haven't talked about binary numbers yet. Right here. Right. I don't think this one, let's be right. Yeah, it does. You're right. Okay, if you look at this here, is that if you look at this number right here, these are all low. 0, 0, 0. You see that they're all low. This one's a 1, this is a 0, this is a 0. Right there. This is a 0, this is a 1, this is a 0. This is a 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, right there. And then we go back to 0, 0, 0, right there. So when we look at binary numbers, we haven't talked about that. This book kind of jumps into it later, but I'm going to go ahead and talk about binary numbers at this point here in order to make that slide make sense. When we look at regular numbers, the number 32, right? This is 2 times 10 to the 0 power. This is 2 times 10 to the first power. If we had another number here, a 4, that is 4 times 10 squared, right? We go through, and the reason we use base 10 is because we got 10 fingers. You know, if we were born with 8 fingers, chances are we would use base 8. If everybody was born with 5 fingers on each, or 3 fingers on one hand and 2 fingers on another, we'd be using base 5. Right there. So we use base 10. So when we look at normal numbers, we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we put a 0, and then we put the 1 in the next column. When we do binary numbers, we do the same thing, only we go 0, 1 right there, and then we put the 1 in the next column right there, and then we do 1, 1, and then we put 0, 0 and put the 1 in the next column right there. Then we do 1, 0, 1, 1, 1, 0, and then 1, 1, 1. These all have leading zeros right there. This is the number 0. This is the number 1, 2, 3, 4, 5, 6, 7. So 3 binary bits will allow us to count up to 7, because now our next one's going to go 0, 0, 0, and that's going to be the number 8, and that requires a 4th bit right there. Right there. So when we look at our binary numbers, this is the counting sequence. So when we go back and look at right here, we're counting from 0 to 7 right there. And then we go back and we start counting at 0. This is a typical 3-bit counter. Up right there is what we're seeing right there. So that there, from this diagram, you can see that all waveforms are high only during bit 7, and then they all change back to low at the end of bit 7, the gray area. So this is a typical timing diagram. We'll be using software to generate these clocks and see what the output looks at right there. You know, again, we can transfer data from one place to another. Here are the 2 ways of transferring right there, and I'm jumping to the book simply because it fills in the information. The slides only have the pictures, so I didn't realize that. And you're having trouble staying awake, aren't you? Right there. I noticed between 3 and 5 people have a really hard time Is that the typical nap time? I know I get tired at that time. There. I'm ready for my nap. Unfortunately, I can't take a nap. You would notice it too quickly. Up there. Okay. We have two ways of transferring data from one place to another. This is serial. Right here, serial means that we're going to go one bit at a time over one line going in this direction. Typically, most serial communications have 3 lines, one going in this direction, one going in this direction, and then a ground between them. So most serial communications has 3 lines. If you use a standard serial 9-pin serial cable, pins 2, 3, and 9, I think, are the ones that are used. I know it's 2 and 3, and I can't remember which one. I think it's pin 9 on a 9-pin up there. Or we can use parallel. Now, let me take a couple minutes to talk about this right here. When we look at this, it looks like parallel is faster, right? This takes 8 clock cycles to transfer 8 bits. 8 bits is a standard byte in digital terms. It's a standard size bit of information. And we'll get into more details. Here it takes 1 clock cycle. Right there, up there. So it would appear that parallel is much, much faster. It looks like it's 8 times faster. And it used to be 8 times faster. But what's happened is, in the digital world, and we're not going to spend much time on it in this class, but when we look at a wire here, anytime we have current flowing through the wire, it sets up an electromagnetic field around the wire. And if you study transformers, have you covered transformers yet in your program? You know what a transformer is? And a transformer is basically 2 coils of wire that are wound closely together, sometimes most of the time around a magnetic core, that you deliberately change the current through one coil, and that generates a voltage in the second coil, right there. So if you have 8 wires that are running parallel to each other through a cable, and you're sending digital information at a very high rate of speed, they tend to cross-talk to each other. So in order to keep that from happening, you have to keep the data transfer rate slow, so that the change, because this current, it's only, when I say that current flows through here, it's when the current changes that these fields are set up. If you have a constant DC current, there's no field set up around it. It has to be a changing current right there in order to induce the voltage right there. That's why you can't use transformers for DC voltages. That's why we have AC coming out of the wall. Back in the 1920s, when electricity first started coming out, there was 2 gentlemen that fought like crazy over which was going to be the standard, AC or DC. The person that wanted it to be DC was Thomas Edison. Most people think he's more famous than George Westinghouse, but George Westinghouse was fighting for AC to be the standard. And it turned out Westinghouse was right, because he could put a very high voltage and transmit it from one place to another, and then use a step-down transformer to get it down to a usable voltage level. In the U.S. and North America, it's 120 volts, volts RMS. In Asia and Europe, it's usually 240 to 220 volts RMS. It's not standard household that's there. And believe me, I know that so well, because I shipped some stuff from the U.S. I had to buy transformers for that there. If I plugged them in without the transformers, I would be letting my motors would all the smoke would go out of them. They would burn up very quickly. That there. So as a result, most communications today is serial. Right there. That there. So, and the reason is that parallel is hampered by crosstalk. When I first started using computer systems almost all hard drives that interface to the computer use something called a parallel ATA, PATA interface. Before that, there was other ones, but they were parallel interfaces between the computer and the hard drive. Scanners would use a parallel port. Printers would use parallel ports. You would have a parallel port on the back of all your PCs, and they would talk to any kind of device that needed high speed. And that would be scanners, printers, or graphics printers. Let's try to think what else that there. Scanners and printers were the big ones, and disk drives, external disk drives. Nowadays, what's the standard interface on your computer going outside? USB, right? USB stands for Universal Serial Bus, right there. So you don't hardly ever see a parallel interface going to a PC anymore. You go inside of a PC, even up to about 7 or 8 years ago, most of the hard drives were still parallel, and they would use relatively short cables, ribbon cables, but they were still parallel. Nowadays, almost every hard drive out there, well, pretty much everyone I know of out there, uses some form of parallel serial ATA interface. So parallel is more or less disappeared when it comes to interfaces outside of the computer system. Now, once you're internal and on the same piece of silicon or on the same board and very close, then crosstalk ceases to be such a problem, and then you will see parallel. So when you look at on a computer motherboard, for example, the interface between the RAM and the microprocessor is going to be parallel. But because you're leaving the motherboard and going to a disk drive elsewhere in the case, it's going to be serial. So the length of the connection makes a difference. How long the connection is, on which one is the more effective one. So typically, right there, it says that the disadvantage of parallel, it takes more lines. They don't talk about here the disadvantage is also that that you're limited by crosstalk when you're on a cable, and crosstalk is a big one that there. So this particular here talks about how long it takes to transfer 8 bits, 80 microseconds, and if you did it, it would be taking 10 for all 8 bits. But again, they don't necessarily get into the concept of crosstalk, and that has become a physical restriction because of the physics involved in running cables. Now, if you can put them 3 inches apart from each other, then it's not a big problem, because then you're away from the crosstalk area right there. But normally they're run in the same cable, or they're run on a ribbon cable. Usually ribbon cables because they're cheap, right there. Okay, so questions: binary, a bit, what are the bits, rise or fall, those are just up there. Okay, now we're going to get into the 3 basic gates right there. So we have the concept of and, not, and or. These are basic logical functions. The particular person, George Boole, the book talks about it right here, in the 1850s, long before digital electronics, he wrote logic statements. Now, he was they say logic and mathematician. He was actually more of a philosopher. And since he was Irish, we probably have to assume he was probably a drunk philosopher. That's there. My parents, or my mother, is Irish, so I know a lot of the Irish bad behaviors. In the 1850s, most academics spent most of their especially philosophers, did most of their thinking at the local pubs. That's there. So he came up with a series of ways of expressing logic statements using symbols that looks like mathematics. You will find that if you look at a number of college course textbooks, not here at UniKL, but if you go to a liberal arts college in, say, the U.S. or Australia or UK, you'll find in the philosophy department there's quite often a course called Introduction to Logic that will teach the same logic we're going to learn here in digital electronics. So philosophy and digital logic have a lot to deal with in terms of that there. So we have the three basic functions right here. These are our three gates. We'll talk about them right here. We have, and let me just kind of jump in here and do it this way. We have the NOT gate. The NOT gate looks like this right here. Anytime you see the bubble, that means you invert the signal right there. This bubble, we'll see that bubble pop up a lot. That means an inversion. If you see something looks like this, that's usually a buffer. There's no bubble. No bubble. Right there. So with no bubble, that means that you don't invert the signal. So if you have a 1 here, you have a 1 here. Here, if you have a 1, you have a 0 here. You have a 0, and you have a 1 here. So 0, 0. So the NOT gate simply inverts the signal right there. So we look at the next one. The next one is the AND. The AND, it looks like this. I'm going to show a 3-input AND gate. And our inputs are A, B, C. I'm going to show my output is X. In the AND gate, X is going to be high only if all three inputs are high. All the inputs, A and B and C, have to be high. Now, we represent that with a truth table. We're going to be seeing truth tables. And our truth tables are going to look like this: A, B, C. And we write our binary numbers. Right there. And I should put my grid on here. And by the way, the reason I use this computer when I record is that it would be a complete waste if I tried recording using a normal whiteboard. So I have to use this computer screen to do it this way. So the only place this is going to be true is here, and everything else is going to be a 0 on the output right there. Right there. And I'm going to pull up some software here. You'll get a chance to use the software later. Right there. Right here. And if I can find it. Oh, it says it's in the start. This is what you can use electronic workbench for this, but for when we do the labs, we're going to be using this software because this also goes through right there. And I'm just going to kind of show you what a timing pattern looks like for this. Right here. I love this computer, but the mouse that they sell special for this thing is really not very good. right there. No. And I'm sorry, I have to do that for a second here. Unfortunately, the screen resolution is so poor with these projectors that I can't see anything on the screen with that there. So we've got this symbol right here, and I'm just going to basically show you how these timing diagrams work here. Right there. We'll get a whole bunch of warnings and errors. That's all right. When we go into the lab, we'll download this to a board. You can flip switches and see it work as well. Okay, product file, new. And these are just things that you have to do every time you do it. And again, as I said, you'll get a chance to play with this software later on, but right now I just want to kind of show you okay, yep, that's fine. A is our most significant bit. So again, we can see there's our timing patterns like we saw at the beginning where I showed you that one right there. 0, 1, 2, 3, 4, 5, 6, 7. It shows that right there. Here's our binary. This is what we see. This is a 50 hertz clock or 50 nanoseconds interval. So at this point, right here, we can see that the only time our output is high is when they're all high. Now ignore this little glitch right there. That's just a little glitch right there. That will actually happen in the real world, and we'll get into that, why that happens in the real world. But as you can see, when we look at this here, this agrees with that timing table that I gave, as long as we ignore this glitch right there. And unfortunately, those glitches is just part of the way the hardware works. And sometimes those cause you headaches. Those are the problems that makes engineering fun. Because I know that I should not get a 1 at that point right there in time, but because of some reason, the way that the chip works, that's there, and really what it is this is high, and this goes from low to high quicker than this one does. So as a result, there's a very short period internally where the output goes high. As soon as this one goes low, is registered low inside the chip, then the output goes low. But because the timing is such that right here, this shows it as if it's happening at the same time, but in reality, inside the chip, it's not. That there, so you get this little bit of a glitch right there. So, and it's going to show up every time. That's just the way. And again, I'm just kind of showing you the way that we would analyze these circuits using it in the lab right there. Right there. And this is the way the simulation would work. And what we would do next, if we were in the lab, we would actually download this to our programmable logic. We'll talk more about that later. But I just kind of, we talk about these timing diagrams. I just want to give you a feel for where they come from, right there. And I created this timing diagram. It took like 5-10 minutes to do that. There, you'll get more opportunities to do that. But there, going back to this right here, that's our AND gate. Our other main gate is the OR gate. And again, B, C. My B doesn't look like that there. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. Did I miss one? Up there, 0, 0, 0, 0, 0, 1, 1, 0. Yep, that's right. Okay. One, two, three, 4, 5, 6, 7, 8. Okay, yep, they're all here. Okay. Now, again, this output is true if A or B or C is high. So the only place this is going to be high or low is here, and every place else is going to be a 1 right there. So I can go back to my circuit right here and delete that. Put in an OR 3. And what did I do here? I'm going to in an ideal world, I should be able to just delete it and put it right back in the same place, but because of my mouse not being very accurate, right there. So there's my OR 3 right there. I just replaced that in the circuit. Right there. And again, you can look at this right here. We don't have to go into much detail, but you can see we still have a couple glitches, but you can see it's only low here and everywhere else it's high until we get to here. So again, our simulation matches what we would expect to see from our truth table right there. So, okay. Okay, we got plenty of time. That's it. I just, like I said, I don't like to go much beyond an hour to an hour and 15 minutes, right, in that time period. So I'm not quite ready to quit yet. So we're under an hour right there. Okay. Let me go back to my book here. I'm kind of ignoring the PowerPoints and I'm just using the book. I skipped fewer things. Now, I have had professors in my lifetime that will put the book up and read the book line by line. I'm not going to do that to you. I'm just kind of pointing out, and if anybody's got a thumb drive, I will be happy to let you have a copy of this, after class of this book. That's there. There. This book costs $130 in the U.S. It's going to be a 600 ringgit book here, so I'm not going to have. And this is a 2 edition back. This is an older version. So, okay. So we've got the AND gate and the OR gate. Those are our 3 basic functions right there. Right there. We have a few other things that we want to look at. That there, a magnitude comparator compares two circuits or two inputs and decides which one is higher or lower. We'll see that in more detail. Right there, we have 9 types of logic. That there, we're not going to get through all these. That there, we have 4 arithmetic. We're going to talk about adders, encoders, decoders, multiplexers, demultiplexers. That there. So we're going to go through a lot of stuff here, and we're not going to do it all in the next 20 minutes or so, but we're just going to kind of hit the highlights there. That there. There. The comparison, it has 2 numbers in here, and these can be anywhere from 2 to 8 bits wide, right there. Going into that right there. We have A and B. Those are our 2 inputs. And our outputs are either going to be A is greater than B, A is less than B, or A is equal to B, right there. So in this particular case, we're showing that we're putting into here 0, 0, 1, 0, and here we're putting 0, 1, 0, 1. So that's the binary code for 2, binary code for 5. And this says that A is less than B, right there. Now, what's inside this comparator we'll look at later, but that's what a comparator does. It just simply looks at two binary numbers and decides which one's greater than the other. Right there. We have multiple circuits there. We'll spend a lot of time talking about an adder. An adder has 2 numbers that go into it. We have not talked about how we add binary numbers yet, so it's a little early to get into that there. But if we put in, say, 0, 1, 0, 1, and we put 0, 0, 1, 0, that's 5 and 2. We're going to get out 0, 1, 1, 1, which is 7, and we get no carry out in this particular case. That's there. Because if we put in, for example, 1, 0, 0, 0, and 1, 0, 0, 0, that's actually going to give us that 16, or 8 plus 8, which is 16, which 16 is going to be a 0 out and a carry out right there. So, and we'll get into more detail, but an adder does exactly what it's supposed to do. It adds 2 numbers right there. In this particular case, this is putting in, the example they give here is that they're putting in 3 and 9, and they get out 12 right there. And we haven't talked about hex numbers, but you know, you would get a binary. So this would be 3, 0, and what's going on here? 0, 0, 1, 1, and 9 is 1, 0, 0, 1, right there. So that's 0, carry a 1. That's going to be 0, 1, 1, 1. This happens to be the binary number for 12. Right there. So it's just simply that there. We're going to be designing a 4-bit adder later on in the class. We're going to go through the design, how we design a 4-bit adder. Right there. Subtractors do the same thing. We're not going to talk about the subtractors right now, and multipliers who multiplies and divide. We can have circuits that do such things right there. Now, keep in mind, you're pulling out your calculator, you're probably putting it in binary note form out there. The best binary to decimal calculator I've seen is the Windows 10 finally, Windows 10 did something right this time. Right there. Because I can go through here, and I can put 9 plus 3, and my equal key is missing. And the reason my equal key is missing because my screen is too small. My equal key is right here. That's 12. You can see there's my 12 right here. That's there. And I can work in binary form. 0, 0, 1, 1 plus, that's 3, and what was it? Plus 9, which is 1, 0, 0, 1. Equals, and there's my 1100, which is decimal 12, or hexadecimal C, right there. So and we're working with that there. So code conversions, I'm not going to talk about right now, but that converts between binary and other codes, such as coded, right there. Now we also got calculator keypads where we're going to figure out which key was hit, right there. We press a key and this outputs the binary code for 9, right there. There's better ways of doing that. The decoding function. Here we put in, this is a very common one, we'll talk about this in more detail. We have our binary input, and out here's our 7-segment display. We're going to say, for example, a 7-segment display looks like this. A, B, C, D, E, F, G. That's how I'm trying to train my 2-year-old niece how to count, for the alphabet right there. And for the number 5, we want these segments to be lit up right there. So, and what this does is it takes that number and it lights up the proper digits for that particular character. So that's a decoding operation. So we've got encoders and decoders. We'll spend a lot more right there. Then we got the multiplexer and demultiplexer. Those are basically used to, we have 3 inputs, 3 outputs, 1 line in between, and we put 0, 0 here, 0, 0 here. So that's going to take this one here, through here, and put it there. We put 0, 1, 0, 1 here. That takes this one through and puts it there. And we put 1, 1. It takes this one here through, like this right here. So it allows us to share 1 wire in between 2 points. The early telephones operated that way. And well, they still operate that way. Up there. You don't have a pair of wires for every phone going from your house to someone's house in Johor. You share wires, and they have to be multiplex and demultiplex. So phone switches are up there. We'll get into storage. Right there, flip-flops and registers are used to store data. Right there, we'll talk about that there. That's where we store data. At there, storage. There, you have data storage. You know, RAM in your computer. You've got RAM and ROM. We'll talk a lot more about that. Counters. We can have counting where we count. Right there. I will design some counters toward the end. So I'm just kind of skipping through the rest of this chapter. This chapter doesn't really have any meat to it. The last couple things on the chapter here talk about ICs and how they're made. Malaysia is does a lot of this work here. Texas Instruments. ChipPack used to do it. I think ChipPack is not there, or StatPack or whatever. I think they closed. But this is the silicon chip. When a IC is made, it's in a silicon wafer that's circular, and then they cut it up into little squares. Each one of these is a chip right there. And these chips are placed in the center, and then these connectors come out from that there, right there. So our IC packages, they can be plastic, they can be ceramic, that there, or they can be other materials. The most common is plastic because it's the cheapest. Ceramic is common in situations where temperature is an issue. A lot of military, industrial electronics has to go into ceramic, especially if it's going to be operated in space. You know, things like that there. If you're talking something that's going to go onto a satellite or onto a spacecraft, then quite often it will use ceramic right there. You'll see the most common package is the dual inline. But you see that we've got multiple types of packages right there. So we've got, you know, the PLCC with the JTAG leads, which you basically put into a socket. These are surface mount dual inlines. These are with no leads. The contacts are part of the case. So you actually make the connections right here. Here is where the connections are right there. So we're not going to worry too much about that there. This gets into this. This is kind of a funky thing here. I'm not going to go into that there. They talk about SSI, MSI, LSI, and VLSI. Small scale integration, something less than, you know, 50 chips, 50 gates or so, or transistors on that there. about 50 transistors, but they say up to 10 gate equivalents. That's an AND gate or an OR gate right there. Then 10 to 100 is medium, 100 to 10,000 very large scale, and then they're saying very large scale is between 10,000 and 100,000. That's all very dated. There's ICs now with millions of gates on them. Millions and millions right there. You know, so ultra large scale, they keep downscaling those numbers right there. I'm not going to up there. I think I'm going to stop at this point here before we get into programmable logic right there, because that's an area that I want to spend a little bit of time on when we talk about programmable logic right there. We really haven't got into this discussion yet of the material, but we're just kind of introduction to where we're going to go with it right there.